Hello, I'm Paweł,
And I'm Grzegorz.
and as the members of the Warsaw University of Technology SIE AeroDesign Club, we would like to present to you our air cargo class aircraft, the Mosquito. The plane has a specially designed cargo compartment for blood transport, a carb weight of 2.4 kilograms, and is able to carry a load of 3.2 kilograms. The aircraft has semi-elliptical wing with winglets to minimize induced drag. As the aircraft is going to be operated from a grass airstrip, the wide main landing gear strut is applied. Our team structure consists of 3 personnel on board: the president, the vice president, and the treasurer. They are responsible for organizing the workspace in the workshop, providing the supplies, contacting with our university authorities and our sponsors. All actions and major decisions have to be consulted with our faculty advisor. Our project routine started with selecting a coordinator who would organize the design, calculation, and testing processes. The construction was carried out by the entire association, supervised by the main coordinator and his team, and the responsibility for logistical and financial matters were under conduct of club's leaders. For work organizations, we used apps like Microsoft Teams or Trello.
We started the preliminary design process in September 2021. The manufacturing process was planned for the end of winter because we didn't want to risk COVID lockdown interrupting our work, and first months were spent on designing, calculations, and sponsor hunting. Unfortunately, the construction of the plane started with a delay due to lack of funds to purchase materials. This was also the first time our club would participate in the Air Cargo Challenge, so this was quite a new challenge for us. Due to manufacturability limitations, we had to keep the balance between self-made and outsourced aircraft elements. Additionally, our own manufacturability capabilities were reduced as some of our tools were stuck overseas after participating in a different competition. Following the competition rules, we outlined the basic aircraft design. Then, scoring analysis allowed us to select the most important parameters, further narrowing down the design.
The rules are strict about motor and propellers, so we started with their selection to determine the available thrust. We tested the purchased motor and propellers in a wind tunnel for various airflow conditions with voltage limits as described in the regulations. Basing on the test results, we have picked CAM carbon propeller, which generates slightly higher thrust than the APC. We have considered low wing, high wing, and flying wing configurations, and after analyzing the pros and the cons, we have decided to use the high wing because of its high stability. The aim was to design lightweight aircraft with good access to cargo compartment. The doors are on the right side of the fuselage. The lightweight fuselage was achieved thanks to mounting tail boom and main landing gear to the wing. In the case of deep stall, the classical empennage was selected.
To establish main parameter of our construction, we used a thrust-to-weight plot. The team assumed that the climb rate and the payload mass would be the most optimal scoring categories to achieve. We performed a score computation in MATLAB and came to conclusion that the optimal climb rate and payload would be 1.8 meter per second and 3.2 kilograms with runway length 60 meters. For the final configuration, we prepared a payload prediction curve considering changes in dynamic pressure and thrust. At this point, close attention was paid to airfoil selection. To achieve high vertical speed, it was necessary to apply airfoil with high CL cubed divided by CD squared ratio. We considered 3 airfoils: Selig 3024, Selig 3320, and PP02. Using AVL and XFLR5 software and analytical formulas, we compared them, and basing on data we decided to use PP02 with 10% thickness and 7% chamber, which stands out with its high ratio.
The team opted for elliptical wing as according to the Mach law, the elliptical load distribution has the smallest induced drag. To minimize 3D flow behind the wing, the straight trailing edge was applied. To improve the butt stall characteristics of an elliptical wing, we designed a geometrical wing twist, so the flow separation would occur lately at the ailerons. To decrease induced drag further, we decided to use winglets. The goal was to get a proportional distribution of an induced angle to the cosine of the lateral inclination angle. We achieved that through the use of twist and Selig 3010 and 9032 airfoils. Using wing tip devices allowed us to decrease induced drag by 10% and increase CL cubed to CD squared ratio by about 15%. Knowing the density of used materials, we performed the mass and balance analysis. During manufacturing, each part was weighed and compared to our expectations to ensure that they meet the requirements. Thanks to such control, we achieved planned mass. Moreover, the aircraft in empty configuration doesn't need any additional balance.
As we decided to maximize climb rate, we needed to have a large wing, and due to size limitations, that left us with a little space for the vertical stabilizer. So instead of classic stabilizer with an elevator, we designed a stabilator. To counterattack a high pitching moment to the main wing, we used a reverse NECA 4408 airfoil to balance it out. Using maximum takeoff weight from the mass analysis, we calculated stability and maneuverability neutral points, and we got 7 to 12% stability margin. We also performed a dynamic stability analysis using XFLR5 software. The plane can dump short period oscillations, fugodoid, roll, and Dutch roll. Pilot's input is needed to exit the spiral, which is not an issue. For structural analysis, we started with choosing the basic materials based on no external factors. Then, we followed an interactive design process to determine geometry, internal loads, and stresses. We used a flight envelope to compute loads on each part of the flight, including loads from steering and gas wing. The maximum load factor is 4.1. Wing and empennage structure was calculated using analytical formulas. As the wing is made of glass and carbon fiber composites, the displacement minimalization was considered.
The wing is a single carbon spar construction with a fiberglass torsion box. Ribs are made of balsa wood with the exception of shrink ribs, which use carbon fiber plywood material. Winglets and blends are made of polystyrene core covered in fiberglass to achieve high smoothness of surface. Trailing edges are covered with aluminum foil to increase the stiffness. The stabilator has a single spar with torsion box, both made of balsa wood. Ribs are made of balsa and plywood. Leading and trailing edges are reinforced with balsa board to add stiffness to the structure. Due to low loads, the structure is covered with heat shrinkage foil. The spar has aluminum tubes embedded into itself, which act as a hinge axis. The fin is made of balsa wood, as the torsion box is negligibly low, a spar carries both bending and twisting. The rudder is made of polystyrene foam covered with aluminum tape. The tail boom is manufactured on the steel core. The structure is made of carbon fiber, glass fiber, and balsa wood. The wings, the empennage, and their structure were glued on the PMAA fixers. For fuselage, we use carbon fiber and glass fiber with helix mid layers to prevent buckling. We considered 3 cargo bay variants and decided to load the cargo from the side to allow for easy access to every bag. Loads from the engine and the front wheel are carried by the plywood frames. The main landing gear is made of carbon fiber composite with balsa core. The front gear has 2 wheels to minimize friction and to provide stability over potholes. Rear wheels were selected based on friction tests, and we chose Cavan Superlight 100mm wheels due to their low rolling resistance and high energy absorption. All wooden parts were cut on our milling machine.
At the end, we verified our initial design assumption with a performance analysis. The goal was to achieve a minimal climb rate of 1.8 meters per second. We performed a set of calculations and the climb speed was a bit over our goal, which leaves a safety margin in case the calculation were too optimistic. Our second goal was the horizontal speed, and during the design process we used all measures to minimize the drag by designing winglets or using the elliptical wing. We also performed a turn analysis to determine if our aircraft will be able to turn within the airfield area. And it seems that even the tightest won't be a problem if we keep the bank angle over 20 degrees at our cruise speed. The team also calculated takeoff run length and verified the calculation method using one of our old aircraft, which allowed us to approximate the takeoff length is in a function of the weight. This year rules turned out to be quite demanding for their aircraft, but we hope that the Mosquito will face this completely new challenge with very good results. This year's project allowed us to gain new knowledge both in designing and management of the projects. Thank you for your attention, and it's time for the proof of flight.